you have any questions? Yeah, it's going to be. I was talking about logistic stuff a little bit last time. Do you have calculators with you? Didn't bring it? Okay, well, I'm going to give out an assignment here in a bit, and it's a big, long assignment. It'll be something that you can take and do. You know, it won't be due till like after we get back. Okay. And you know, it'll be after break. And I thought we'd talk a little bit about that. Uh, yeah, Thursday and Friday next week. Yeah. It's just really messing up one of the other courses I'm teaching, so it's uh, just turning out to be a really, really bad semester for me. The smart board is broken. Oh, please don't be broken. No, it seems to work for me. Okay. I don't know. There's a sign that says it's broken. It seems to work. Yeah, it's always worked. So there's some others that are broken that I don't think they've labeled, but this one seems to work. We're going to be doing something on the calculator, and I talked about this the other day about what's called the logistic function, and basically, let me back up a little bit. Insert an extra page here. Suppose we have some sort of quantity or some population. Let's do population. It doesn't have to be a population of things. This should just be some sort of quantity. Okay. Exponential growth or decay is when we have the rate of change of p with respect to time is some constant times p. And I did this the other day, so this is all kind of review. If k is greater than 0, we have something like that. If k is less than 0, we'll have something like this. And you solve that. The reason it's called exponential growth or decay is if you solve that, the solution is p of t is some constant, is to some constant e to the kt. So, and if k is positive, it's going to increase without bound. If k is negative, it's going to decrease and head towards 0 as time goes to infinity. And that's sometimes called a pure growth process. And one of the things that you can look at is as a population growth model that's purely exponential, which they call Malthusian, from Malthus. On page, and I know I skipped that real fast, but we'll come back to it here. On page 97, we have the U.S. population from the census that was given from 1790 up through 2010. And I just picked some of the dates out of here. 1790, 1820, so I went like every 30 years from when the first census was made. And T is going to be how many years after 1790. So our first census in the United States was taken in 1790, and the population over here is in millions. Let me make my so T is years after 1790. And P of T is millions, so in 1790 there were 3.9 million people in the U.S. according to the first census. Well, what I want to do is to put this stuff in the calculator. And sometimes the calculator works on this. And sometimes it doesn't. Let me see if I can pull it up here. Last time I tried this, it didn't work. It's not going to work this time either. Okay. Which I don't understand because it works. I put that calculator program on the H drive, which is accessible all over campus, and I go to the room, a different room in this building, and it works fine. So something about this computer. So what I'd like you to do, you can use mine. Okay. Don't know what's in there. Is I'd like us to put this in, and I had a feeling this wasn't going to work, but in case you don't remember how to do this, you want to go to Stat, Edit. Okay. So you go to Stat, Edit, and it will pull up the L1 and L2, and we want to enter those numbers in for L1 and L2. And I'll let people do that. Let me pause things while folks enter those numbers. So we've entered those numbers into the lists. L1 is going to be T, L2 is P. Put in those numbers. We're going to be using the calculator to generate some functions for us. And if you put 1790, 1820 and stuff like that in there, the numbers are going to be too big for it, and the program will just kind of freeze. So put in 0, 30, 60, 90 down for L1 and 3.9 up to 281.42, how many million people there were in 2000. And put those in, one for L1 and one for L2. Now we're going to graph these, and since you may not have familiarity with that, what you want to do is, well, first thing, I don't have it said here, is go into the Y equals menu and make sure everything is cleared out, that you don't have any functions in for Y1 or Y2. Okay, so just hit clear. It's gone. Yep. So make sure there are no functions in for Y1 or Y2 or whatever in your Y equals menu, because the calculator get all confused at that point too. So once you have those cleared, go to stat plot, which is second Y equals, I believe. And you want to select plot 1. And I've got up here in the right hand corner what that should look like, at least on a TI-83. Okay, so we're selecting plot 1. You want to, once you've done that, go down to the on-off thing and hit enter on that. And we want to graph, we're just going to plot points. So that's the very first type of graph. So move over to that and hit enter. Then make sure your list of your x-values is on, and it'll make sure it's on. And because I want things to show up pretty well, let the mark be the little square. Okay. I don't ever use the plus or the dot unless I'm graphing more than one thing at one time. Okay, so the next thing is we want to graph these points and go over to, okay, zoom, hit the zoom button, and now go down to zoom stat. What that does is that will automatically set the X max, X min, and Y max, Y min, so that it matches up what you have in the list. And then Does it graph? And does it look like the graph I have there in the middle? Okay. All right, now, to this thing, okay, you go to second up here, stat plot. Yeah. So this is the y equals, but second stat plot, hit plot 1, and if you've got plot 2 or plot 3, you want to turn those off. Okay. And then hit on the scatter plot, which is the first thing. L1 and L2 are their x and y values. The mark is the square. Then go hit the zoom button and select zoom stat. On the 83, it's number 9. I don't know what it is on other, but go down to zoom stat. And I don't know whether you have to hit the graph or not, but when you do, you get this thing. Now, you may not have the same marks along the x and y axis. I think I went in there and chose the x-axis to be about every 20 or so. You probably should let them be every 30. They would match up with the points. And the y's to be about every 50 or something like that. The marks along the x and y axis aren't that terribly important. We're not really going to be reading things off from that. Okay, now this looks, if you're thinking about what exponential graphs look like, this looks like it might be an exponential graph. Okay. It seems to just keep on going up. So we're going to let the calculator draw one for us. So let me get rid of that. What the calculator has built into it is a number of programs that will fit a curve to the data you have. And if you go now to stat and go over 1 to calc, and you'll see a big selection of choices there. Somewhere down here is this one, exponential regression. Now, it's really interesting to know what the calculators do when they do this. There is a standard way of coming up with a straight line, the best fit straight line, which you may have seen in stat, called the least squares regression line. And basically what these things do for exponential regression is they take the data. If this is an exponential curve, then if I took the logarithm of this, it would be flat. So they take the logarithm of the data, fit the best possible straight line to that logarithm, and then take the inverse of that, which is raise it to the exponential, make an exponential out of it, and see what you got. So I went to a conference, technology conference one time, and one of the people there explained what all the calculators do to come up with these regression things. But press exponential regression. Now, what should come up is a screen that just says exponential regression. Now, what I'm going to do now, you don't actually have to do this. You can do a lot of things manually. But I'm going to set this up so that the calculator automatically computes the curve and plugs it in to your calculator so that you can graph it. So you would type exponential regression. If you're going to, if you just type exponential regression, it'll compute this thing down here, but it won't do anything with it. It automatically goes to list 1 and list 2, but what I want to do is I want to make it automatically plug things into Y1. So you should, it says exponential regression, go on the calculator, and what is it, alpha or something, that takes you down to L1. L1's, no, second. Yep. Okay, all right. Yeah, if you got, actually you don't have to. So this is for a TI-83. If you got a fancier calculator, okay, then it'll automatically do L1 and L2. Okay. I forgot about that. Okay. What you do is just a second. Let's let Harold catch up with you. Is okay on the TI-84 pluses. When you press exponential regression, it'll automatically come up a screen, and it should say XList L1, Y list L2, so you don't have to do anything. Then when you go down where it says store, then you know, go down to the store. Now you need to enter Y1. Now Y1 is, to get to Y1 you would do vars, variables. Okay. Then you would do function. Excuse me. Yeah, function. And select Y1. Okay. And once you do that, you're ready to calculate. Don't worry about that. Yeah. Yeah. It's the frequency list is not necessary. We want every one of these points to be just up there once. Okay. So it automatically, the frequency list do that. So once you've got that, you need to go down to the store regression equation. Oh, that should be L1. So we need to put second. Okay. Now just go down to that, and then you want to do Y1, which is variables. Y variables function. One. Yeah. Okay. Then you hit calculate. Go down to the next one and go calculate. Yeah, I'd forgotten that the TI-84 pluses have a very different screen. Did it give you the equation? Okay. Now, don't worry about the R values. Your calculator may or may not show an R value, and we're not worried about that. You might remember from statistics it had to do with how well the correlation was. Now, it should have also plugged in, go into your Y equals menu. It should have plugged that equation in for Y equals, did it? Okay. Now graph. Okay. I hope you get something like the screen I have there. So it looked a whole lot like an exponential, but the best exponential that fits this is below the points and then above the points. And also, what's going to happen to this exponential function? As time passes, the U.S. population is going to run off to infinity, which doesn't really sound like a very likely scenario. So this exponential graph may fit some of these points pretty well, but it doesn't fit the other things very well. Okay, so hold on to that. We're going to come back to it. Okay, did you have that graph? And as you can see, it doesn't match it real well. There's another type of model that's used a lot in population. That's what's called the logistic model. And I mentioned this the other day, and there's all sorts of ways of getting to it. But basically, logistic model is that the rate of change of the population with respect to time is, and I'm going to have the constants all wrong, so don't worry about it. This is a constant times p, which is the exponential model, but then times something, what did I call it the other day? I don't know. I don't have my notes. I don't remember what I called it the other day, but p times p minus 1. That's what I had here. And there are other formulations of it, but the rate of change is not a constant times, it's not proportional to how many people there are, but it's proportional to how they interact with each other. So this is, it probably should be worded a little differently. I think it's, slightly. Formulation. Yeah, they have it. This isn't wrong. It just kind of depends on where you start here. Their formulation, I'm going to change what they have too. They have it's some constant times p times p1 minus p. And I mean, depending upon what you call your constants, you can write it all sorts of ways. The point is that this is A and P1 are constants that are particular to whatever you're looking at here. And the cap, and so you're meeting with, it's how one group of people interacts with the other people. So you might think of this as, if we're talking about the males and females or something, everybody else. So the rate of change is not proportionate to how many people there are, but how they interact with each other. Okay. And I talked about what a logistic looks like. I'll draw another picture here in a minute. But, we're going to look at the logistic function that best models this data. So go back to your calculator, and we've already got everything entered. Go over here, go back to stat calc. Color here. Stat calc to get to this one, and somewhere down here is you're going to see a term called logistic. And hit enter. Okay. Now, I don't know, this is what the TI-83 looks like, but it probably comes up like the screen before. Make sure that you're looking at L1, L2, only don't, well, if don't put this in Y1, put this in Y2. Okay. Yeah, that way you'll have both graphs right next to each other. Because you already got the exponential in for Y1. And so select Y2 just by going to variables, Y variables function, and go down to 2. Now, the logistic takes a while to come up with, because the equation for a logistic, and I'm going to write this in terms of P's and T's because that's what our variables are. It would be P is some constant over 1 plus another constant, E raised to some negative constant times T. And it takes a while. And once you do that, hit the graph. Now, what you may have is, if you have the old function, it'll be doing this. But this new the logistic function should do a lot better job of going through those points. Did you get it? Okay. Do you still have Y1 in there? It's going to be Y1. Okay, so they both should graph. Okay, then so go to logistic. Uh-huh. Okay, just let it. It takes a while to do this. All right. Now see. Now go to Y equals. See if it's. Okay. Well, what did you? Yeah, yours worked. So I don't know what the deal is. Go back then and delete it. Yeah, delete both of them. Yeah, delete both of them. Yeah, delete and Y1. because it's just copying that graph or something. Just be clear. And now try it with y1. Okay. But what you get is a function that really matches the data a lot better. And what I did, about better than the exponential, what I did was extend the window. Is okay, the current window only goes to about 100 and how many? Only goes to 210 years after the first one. So what happens in the long run? So I extended my window, my X max, to 500 to tell me what's the U.S. population going to do like 500 years after the first one. And I extended my Y a little bit upwards. And if you look at this time, you'll see that the logistic equation comes up and starts to level off. Where that levels off is very important. That's called the carrying capacity, okay, which you can get by taking the limit of this thing as t goes to infinity. And I'm going to ask you to do that for the problem I've got. Also, there's some very important places here on this graph. On the logistic function, things are very steep, and then they start to level off. They're always increasing, but there's a particular point here somewhere where it stops going from concave up to concave and starts going concave down. This inflection point is really important because that's where things start slowing down. So if this model is a good model for the U.S. population, then we could take this function here, take the second derivative and set it equal to 0. It's not a whole lot of fun, but you can. And figure out where the inflection point is, because that's what the second derivative tells us. And that would tell us that at that particular time, the population, it's still growing, but it's not growing as rapidly. So that would mean that's kind of that's an important place. Logistic functions also describe, it can be used to describe, say, the result for studying for an exam. At some particular point, it's kind of you have diminishing returns. You're still getting better improvement, but is it really worth it to keep on studying? Not for the amount of time you're putting in. And the same sort of thing too. If you're if you're in marketing and you're marketing a new product, you'll want to run your advertisements until you get this point, because from there on, the ad won't buy as many new customers as before. So that's the inflection point on logistic function turns out to be pretty good. Okay, so let me pass out this, and for those of you that aren't here, I'll put this on Moodle. This is a project that I have used, and I don't have it on the screen, but I have used before. Okay, and it's going to give you some points on the next test. And it talks about the logistic function. Now, I have a little different formulation of it here, but we're looking at it from an epidemic from the point of view of differential equations. And we're thinking about either people are infected or they aren't. And I wish I had, I don't have this on here. Worth putting it up there. But let me write something here so that people that are at home we have this differential equation. dP dt is P times A minus B. P. Okay. So P is going to represent the population. This is the number of people infected by something at time t. Now this is a cumulative result, so you may stop feeling the symptoms, but you still got it. So it would be, for the data I've got a little further down here has to do with the flu, the H1N1 flu virus in 2009, 2010. And so it was a number of people that had had the flu up to that point. Some of them may over it, but they're still counted because it's accumulative. We're looking at how many people had it. And the rate of change in the number of people that have had it is going to be proportional to it's going to have something to do with how the people that are infected interact with the people that aren't infected. So at the very start, the population is going to go rather slowly because you're not going to have very many people infected. Then it's going to pick up rapidly. But the more and more people that get infected, okay, the bigger this number gets, the smaller that number gets, because these are and so the infection rate starts slowing down at that point. Okay, so that's what's going on here. Is the rate of change is proportional to the way that infected people interact with non-infected. And these constants, A and B, have to deal with, well, what size is the population, the whole big population, how easy is it for this disease to be transmitted, that sort of thing. How easy is it for an infected person and a non-infected person to actually meet. Okay, so that's all kind of explained here. What I have a little further down is a horrible-looking logistic function. Okay, which I want you, so I want you to solve this differential equation. It is a separable differential equation because what you're going to have is a very simple looking start, because when you separate this, you get all your p's on one side and your t on the other. You're going to have to do that because it's separable. As you see, the direction is to solve this differential equation. It says use a lot of algebra relations to put it in a particular form. Okay. Then I've got some slope field stuff for getting some feeling for what does a DE like that look like. Okay. Then I've got some little calculus things for what does a logistic function look like in calculus point of view. And then on the back, I have some data for the H1N1 cases reported to the Centers for Disease Control every 2 weeks during the first 14 weeks of the 2009-2010 flu season. Okay. And what we just did with the U.S. population, you'll do with this. Plot it on the calculator. Let it logistics function. It'll try to fit a logistics function to it. See what that looks like. Okay. Then answer some questions. How many people could you be expected to get infected? Okay. Where's the inflection point? What does it mean? So it's a nice little exercise. Sometimes you try to make up something on your own, it doesn't work very well, but this one worked really nicely. Okay, now that's all we're going to do today. Yeah, it's going to be, because we just meet once next week, and I want to get in. I'm actually going to skip on over into chapter 4. I spent about an hour and a half working on some stuff in chapter 3 to use today, and got three-fourths of the way through this explanation of what's what. So we're just going to cover a little bit, a section and a half or so of chapter 3, and we're going to get on into chapter 4, which is some second order linear DEs and applications there. So it'll be a little more interesting with that. Okay. Sometime, right? Okay. No questions about that? Okay. Well, then we'll see you. It's the 17th. Yeah, not Tuesday, but the Tuesday after that. and it's pretty straightforward.